Okay, everybody, so we just completed 10-1. So we're going to jump back and forth in these next couple sections. So we're going to do 10-1, then 11-1, and then 10-2 and 11-2, and then 10-3 and 11-3 because they're connected. So let's take a look at 11-1. So hypothesis test for the difference between means and independent samples. Look familiar, right? Perform a hypothesis test for the difference between two means using the p-value method. Perform a hypothesis test for the difference between two means using the critical value method. So first we're going to take a look at the difference using the p-value method, and we begin with an example. The scores of the National Assessment of Education Progress Mathematics test range from 0 to 500. In a recent year, the sample mean score for students using a computer was 309. The sample standard deviation of 29. For students not using a computer, the sample mean was 303 with a standard deviation of 32. Assume there were 60 students in the computer sample and 40 students in the sample that didn't use a computer. Can we see that the sample mean scores differ by 6 points? Or can we say that 6 points. Okay, now we're interested in the difference between the population means. So, is it plausible that the difference between the population means could be 0? How strong is the evidence that the population mean scores are different? So this type of an example is a situation in which the data of two independent samples. The two samples are independent if the observations in the one sample do not influence the observations in the other. So the issue is whether the mean scores from both populations of students, those using the computers and those without, are equal. So in other words, does mu1 equal mu2? The null hypothesis says that the population means are equal. Alternate hypothesis, there are three, because there are three circumstances. The first one is that mu1 is less than mu2. The second one, mu2 is greater than, or mu1 is greater than mu2. And the third one, that they're just not equal. So we're going to use the following notation. We have mu1 and mu2 for the population means. We have x bar sub 1, x bar sub 2 are the sample means. We have s sub 1 and s sub 2 are the sample standard deviations. And we have m1 and n2 are the sample sizes. None of these are new. We've known these for a while. So this test statistic is based on the difference between the two sample means. So this would be the difference between the two sample means. And the mean of the two sample means is the mean of the population means. So we approximate the standard deviation with the standard error using the formula that we have. We take the difference between the means of the standard error. That will equal the square root of the sample standard, or the sample variance, divided by how many are in our first, and the sample variance of the second divided by how many are in the second, and then add them. After you add, you're going to take the square root. So the test statistic will be the difference between the sample means and the difference between the population means. Those two things, the difference of them, are what we're going to look at. And that'll be divided by our standard error. The degree of freedom will be the smaller of the n sub minus 1, n sub 1 minus 1, and n sub 2 minus 1. So whichever degrees of freedom is smaller in the sample. So we're going to assume that we have simple random samples from two populations. We're also going to assume that they're independent of one another. And we're going to assume that the sample size is larger than 30, or we're told that the population is approximately normal. So we're going to state the null and alternate hypothesis. And if we're making a decision, we choose a significance level. We'll compute this test statistics and compute the p-value. For the left tail, the p-value is the area to the left. For the right tail, the p-value is the area to the right. And for the two-tailed, the p-value is the area to the left and to the right. So we're going to interpret the p-value, making a decision to reject the null hypothesis if the p-value is less than or equal to the significance level alpha. Then we'll state the conclusion. So here we go again. We have the same example we just looked at. First, we're going to check the assumptions, and we have two independent random samples. Both sample sizes are larger than 30, so our assumptions are satisfied. And under the assumption that our null hypothesis is true, the test statistic would be the difference between the sample means minus the difference between the population means all over our standard error. So when we plug everything in, we will get 0.953. Now this is a two-tailed test, so the p-value is the sum of the areas to the right of 0.953 and to the left of negative 0.953. So using technology, we will get the p-value of 0.0 or 0.343. Since our p-value is bigger than 0.05, we do not reject the null hypothesis at the 0.05 level. So there's not enough evidence to conclude that the mean scores differ between those students who use a computer and those who do not. The mean scores might be the same. So using technology, we're going to do the, two sample t-tests. We're going to put in our statistics, and our two sample t-tests, we're going to put in our values here, and we will get the p-value of 0.343. Performing a hypothesis test for a difference between the two means using a critical value method. We're going to state the null and alternate hypothesis, choose a significance level, compute the test statistic. All this 1, 2, 3 are the same. We're going to determine to reject if we have the critical value is negative T alpha, has an area to its left. Reject if T is less than or equal to negative T alpha. The right tail is a critical value T alpha, which has an area to its right, and we're going to reject it if T is greater than or equal to the negative T alpha. The two-tailed tests are T alpha over 2, which has an area to its right, of negative T alpha over 2, which has an area to its left. Reject if the T is greater than T alpha over 2 or T is smaller than negative T alpha over 2 and state the conclusion. So the first three steps are exactly the same. Here we have some data, and we're looking at treatment of wastewater, which is important to reduce the concentration of undesirable pollutants. One such substance is benzene, which is used in industrial solvent. Two methods of water treatment are being compared. Treatment 1 is applied to 5 specimens of wastewater, and treatment 2 is applied to 7 specimens of wastewater. The benzene concentrations in units of milligram per liter for each specimen are as follows. How strong is the evidence that the mean concentration is less than treatment 2 for treatment 1? Then treatment 1. So this is an example where data consists of 2 independent samples. The samples are independent. We know that one sample does not influence the other. First, we check our assumptions, and since they're small, we have to check the skewedness. So we're going to make our number line, put in our dots, and make sure that nothing is skewed in either direction, and there is no evidence of skewedness in either one. So now we have the null hypothesis, to where we're saying that the mean of the first one is equal to the mean of the second. We'll find the critical value in table A3. The sample sizes are N1 equals 5 and N1 equals 7. For the degrees of freedom, we use the smaller, which is going to be 4. And because the alternate hypothesis is right-tailed, the critical value is the value with the area of 0.05 to its right. And we will consult the table A3 with 4 degrees of freedom, and we're going to find that T alpha is 2.132. So we have all these numbers now. We have our data for our sample means and our sample standard deviations. We have our sample sizes. And under the assumption that the null is true, so the value of the test statistic will be, as we found before, we're going to take the difference between the sample means minus the difference between the population means, all divided by our standard error. This is a right-tailed test, so we will reject it if t is greater than t alpha. So because t ends up being 1.590 and 2.31, 2.132, okay, so we have here 2.132, and then we have 1.590. So there's not enough evidence, and we do not reject the null hypothesis. So again, we say not enough evidence to conclude that the mean concentration with treatment 1 is greater than treatment 2. The concentrations might be the same. So what we should learn from this is how to perform a hypothesis test for differences between two means using the p-value method, and how to perform a hypothesis test for the difference between two means using the critical value method. All right, so this is 11.1, and this will end, I'm not sure what day, maybe Tuesday, and depending on how many videos you're going to try to get in today, this might take you into Wednesday. So the next one will be 10.2, and I will talk with you soon.